In the beginning of the class, I showed you that can you hear the shape of the drum? This was the question we raised. Can we hear the shape of the drum? If somebody is playing a drum somewhere, can you tell that what was the shape? Whether it's a square, whether it's a rectangle drum that person is playing, how big the drum is, like how small, how big that drum is. That can we do all these things? Can we analyze that thing? And we gonna try to answer that question. That's a very famous question, but we will start from, can we hear the shape of the guitar string? So this is how the guitar work. If you want to digitally play the guitar, so maybe next week I will show you some math lab simulation of guitar, how digitally do that. So this is how the guitar work. So guitar, the string of the guitar is attached into point, basically fixed into point, and then you pull the guitar. That's the initially you pull the guitar string, and it start vibrating. Then it start going up like down, this like and do in time. So as the time evolved, the this phenomena runs back and forward. It's go like this vibrations in this thing. So how mathematically these vibration can be captured is by this equation. We say utt. I'm not gonna drive that, but we can also drive this equation. Utt, two derivative of t variables in that function u, which is a function of x comma y, and c square. C is a constant which depend on this string. What type of string is, how thick, and what material is used. All these things depends on this. And then gonna be u x x, two variable in x, where u is a function of x and t. So this is a function that will tell you what is the shape. This is basically tell you the shape of string at time t. So this profile, this function, like suppose if I plug t is equal to 0, x and t is equal to 0, my string is at initial position. This is how basically I pull it, and now I'm gonna release it. So now when I will release it, the time will evolve. Let's say let's time at x is equal to 1. The string is like here. So this is the shape of the string. So this function gives in x and t, it gives you the shape of the string at time t, where it is basically how many sine, cosine, or how many uh, simple harmonics the equation says it is going to depends on that. But this whole thing is, so if you want to get that function u of x, you have to solve that equation. Utt is equal to c square u x x, and they're supposed to have some conditions also initially. So you say the initially when x and 0, the shape of the string is f of x. So this is much initially you pull that string, and then you have to have also initial velocity. You will see that this conditions we needed, otherwise we wouldn't be able to find. That's gonna be a g of x. This is an extra condition we have from the heat equation. Heat equation and only this, but doesn't have the derivative of thing. But this time is second order in time also. And then you have that a string is attached at 0t and at maybe 1. If the length of the string is 1 unit, then I will put 1. Let's say the length of the string is L unit. L at t is always 0, because this is a x-axis and this is a u, then this is attached. So basically at when x is 0 or L, so this is a 0 and this is a L, the string. So the profile is always 0 at the, because this is a fixed into the 2 point. So this is a heat equation which is a virtual boundary condition. So these are the boundary conditions. So this is equation number 1, this is equation number 2, 3, and 4. So 1 to 4 is a heat equation. Let's begin by solving this equation. The first I will show you the separation of variable solution, and then I will show you a different solution which will be easier than separation of variable. But when we do the separation of variable, our solution is going to be written in a real Fourier series. But when I do the another one, our solution will be written in the complex Fourier series. So I will give you two different solutions. Uh, Today I'm gonna give you the separation of variable solution, which is a real Fourier series solution. And then on Tuesday, I will do a different way of writing down the solution, which will be a lot easier, but there are some calculation formal, so not rigorous. So we will see that too. Okay, let's start from the separation of variable. But before we start, we need to write down what is the date today. What is today? April 23. Okay. And then we also on Tuesday I will show you that how you can hear the string. How can you tell that how long this string was, and how short, and what was the shape of the string when you hear the sound of the guitar. So that will be on Tuesday. But let's start from separation of variable. So derivation of the solution. So we're gonna assume, the first thing we're gonna assume is we want to find a solution which can be separated, in x and t. It can be written as the product of function of x. So this is x is, when I write x, it means s of x is a function of x. When I write t, it means t is a function of t. So I just don't want to write x all time, but when I say that x, it means it's a function of x and t. So like suppose this function is for example, this function is look like a t square x square. So this is the product of two functions which can be multiplied. But I'm not looking for the solution of this form, x plus t. This function cannot be written as a product of two functions. So that's why this was a very special solution, which is the product of two functions. But this question as a solution which can also is in a different form, cannot be maybe written in x and t also. But we are only looking for a solution which can be written as a product of two function x and t separately. So what I'm gonna do is I'm gonna plug that one into my equation number 1. So plug this in equation number 1. If I plug that in equation number 1, I have two derivative in time. So when I take the derivative, it's gonna only hit the derivative in time, same as we did in the heat equation. And this is a c square and two derivative in space, because it's a partial derivative. So you see that utt is equal to c square uxx. So if you taking the partial two derivative of this function in t, so this is the x is a constant, it's gonna get out, and you're gonna only hit the derivative in t. And same thing is you're only gonna hit the derivative on x on this side. So I'm gonna divide by x and t on both sides. So it's gonna be a t divided by t is equal to c squared double divided by x. So this step is divide both side by divide both side by xt, because x is gonna cancel out when you divide this side and t, or you can say move x on the other side and t on this side. For the simplicity, I'm gonna move the c on the t side. You don't have to. Last time I didn't do it, but it simplifies some calculation, so I'm gonna do this. It's a very similar step which we did the last time. Now, since this is a function of t and this is a function of x, so x and t we can choose independently. So this is a sort of doesn't depend on, like there is no dependence on t here. So it means this is a constant. You know, this is a constant because this is has no dependence on t, and this is a constant because this is equal to that which doesn't have any dependence on t. So both are constant. I can let this is equal to some lambda, where lambda is a constant, where lambda is a constant. Okay. So from there, this implies I'm gonna get two equation. I'm gonna get first equation x double prime is equal to lambda x, and I'm gonna get the second equation t double prime, which is sec2 derivative of t, is equal to c square lambda t. I can solve both equation because this is a ODE, ordinary differential equation, ODE. You know, it's a linear ODE into, yeah, basically second order, and this is a ODE. So you see that the root of the auxiliary equation of this equation is r square is equal to lambda. So r is equal to basically plus minus square root of lambda. So if you want to write the solution of this equation, is going to be x of x, some constant, let's suppose a1 e raised to power square root of lambda x plus a2 e raised to power minus square root of lambda x. This is your math 290 class, you know, when you write down the solution of linear ODE of second order. And the root of this equation is a little different. You know, if you do that one, it's gonna be r square is equal to c square lambda. So r is equal to plus minus square root of c lambda. So therefore, the solution in t of t is gonna be some constant b1 e raised to power c square. I can pull out this c square root of lambda time t plus b2 e to the power minus c square root of lambda time t. Okay, so these are the solution of x and t. All we need to know is now, we need to do is next goal, we just need to find, a1, a2, b1 and b2, which are constant, you know, a1, b2. We just need to find these one. Then we have the solution of our wave equation. You know, that's what we need to do. So I will consider different cases, you know, and on the basis of these cases, we will see that, because we also need to find lambda and lambda, because lambda is also need to be, because lambda is also known, and lambda. So again, I will consider different cases. The last time we did case number 1. What if lambda is 0? If lambda is 0, then x, then let's see if the lambda is 0 here, what is gonna happen? Is gonna have a double prime of x is equal to 0, you know, and double prime of t is equal to 0. But this will give you that x of x, if the double prime of x is 0, it means x is of this form, you know, a sum ax plus b. Now, if you take the integration twice, you're gonna get that. You know, means first derivative is a constant, and then you that constant integrate again. You're gonna get bx plus c definitely. But we have impose the niche boundary condition. Boundary condition. Boundary conditions say that uh, 0t is equal to 0 and ult is equal to 0. So this implies x of 0 times t of t is equal to 0 and x of L and t of t is equal to 0. That implies x of 0 is equal to 0 and x of L is equal to 0 because t cannot be 0. If t is 0, then the solution is 0. So if we don't want, so x is 0. So now if plug these things here, so if x of x is 0, x 0 is equal to 0, this implies a times 0 plus b is equal to 0. This implies b is equal to 0. Okay. If that is the case, it means your solution is x of x is just is equal to ax. But now you have x of L is equal to 0. This implies a times L is equal to 0. L is the length of the string which cannot be 0. Therefore, a is equal to 0. If x a is equal to 0, it means your solution is 0 solution. You know, if that is equal to 0, this implies u x and t is equal to 0 because u x t is a u of x and t of t, which is equal to 0. This is a non-interesting solution, so we are not interested in that solution, but it is a solution 0 0. So which is basically same case between the heat equation when we set lambda is equal to 0. Now we consider the case when lambda is strictly positive. This is the case number 2. If lambda is a strictly positive, and what is the solution of that equation is, yeah, x of x. I'm gonna rewrite that solution again. X of x is equal to a1 e raised to power square root of lambda x plus a2 square root of lambda x, you know. And then you have t of t. We may not need this one, but I'm gonna just write it. Plus t of t raised to power square root of lambda t. So now we have again, we're gonna say x of 0 is equal to 0. That's also we have, and then we have x of L is equal to 0. We're gonna apply these conditions. So it's gonna give me a1 plus, if I plug x is equal to 0 here, you know, it's gonna be a and a2 is equal to 0. And if I plug x is equal to L in the first one, it's gonna be a1 e raised to power square root of lambda time L and time a2 e raised to power minus square root of lambda time L. This is a homogeneous system, you know, where this coefficient is non-zero. You see, this is a non-zero and different than 1. So this, because if L, this can only be 1 if L is 0, but if the L is not 0, this is not 1, and we know that L is not a 0. So this is a homogeneous system which has only solution A and A2 is equal to 0 0 solution. So because you can see that for any values of lambda, when lambda is strictly positive, so L is strictly positive, this number is not 1. And this number is not 1 because this can only have solutions if the coefficient are same or multiple each other. So it's not happening. So this is a 0 0 solution. So this situation gives you means x of x is equal to 0 solution, you know, with a1 and a2, and that will give you x of t is also a 0 solution. That is case is also not interesting to us because that's only give you the 0 0 solution. It's very similar to the heat equation solution. Now the case number 3, which give you something. That case is when lambda is strictly negative. What I can do is I can say, let's suppose lambda is equal to some gamma minus square of that. Just use this way so that you can do this calculation easily, because this number is gonna be strictly negative. It's the square of some number. Doesn't matter what is the gamma square of that number. Then there is a negative sign, so it's gonna be negative. So I just use that one. Let this thing. Then we have a solution. X of x is equal to a e raised to power square root of lambda x plus a to e raised to power minus square root of lambda x. So if I plug that one here, so a of x is gonna be a time e raised to power minus square root of minus is gonna be I, square root of inside is I gamma x, and this is gonna be a to e raised to power minus I gamma x. So you see that the square root of minus gamma square is equal to the square root of minus 1 time square root of gamma square. This is the I time gamma. Okay, so this is and then we have imposed the initial condition, boundary condition, impose boundary condition. So if I impose the boundary condition, boundary conditions are x of 0 is 0 and x of L is also 0. These are my boundary condition. So x of 0, 0, it means a1 plus a2 is equal to 0. And this means a1 plus e raised to power I gamma x time a2 e raised to power minus I gamma x is equal to 0. L, sorry, because I'm plugging L, this boundary condition. L, I'm plugging x in term of place of L. This equation give me a1 is nothing but this is equal to a2. So I will plug back that equation here. So I can get a1 e raised to power I gamma L minus a1, because a2 is also minus a1, e raised to power minus I gamma L is equal to 0. This gives me a1 is equal to e raised to power I gamma L minus e raised to power minus I gamma L is equal to 0. And this calculation will give us a1 time, if I substitute the value of the exponential in terms of sine and cosine, is going to be a cosine gamma L plus I sine gamma L is going to be a negative sign here, and then is the cosine gamma L minus I sine gamma L is equal to 0. This will cancel out that. So you have 2 a1 2I and 2I a1 sine gamma L is equal to 0. You can divide these one over, gonna be a sine gamma L is equal to 0. Therefore gamma L is nothing but this is equal to n pi, where n is any integer. Sine is 0 at n pi. Therefore gamma is equal to n pi divided by L. This implies gamma square is equal to n square pi square divided by L square. And what is a lambda? Lambda is equal to minus gamma square. So if I to that is going to be lambda is equal to minus n square pi square L square. This is gives you, these are the eigenvalue. And this will tell you that, do you see that the eigenvalues depend on the length of the length? This is a very interesting observation here. The eigenvalues depend on the length of the string. So here is the instrument where you can hear the length of the string from these eigenvalue, you know, because n is, what is n? N is going to be the how many number of simple harmonics you need in order to produce that sound, you know. So once you hear n, you know, if you hear n, then you can hear L. If you know what is a gamma, you know, if you know what is the largest value of the gamma, is one is the largest eigenvalue, so you can hear the string of, basically you just can find L. So here I do some, so L is equal to basically is gonna be minus n square pi square divided by gamma lambda, you know. So that whatever, like if I know what is the maximum, if lambda is let's suppose less than or equal to, this is the largest eigenvalue is less than, let's suppose 20, it means 1 over lambda is less than is equal to 1 over 20, you know. So if you plug that one here, you can say that is going to be minus n square pi square over 20. So it means the length of the string length is less than that number, depending on the harmonics, how many harmonics you add into it, you know. And you know that the Fourier series sometimes converge really fast. You can suppose like n is equal to 20 is the best sound you can get from your harmonics. So just choose n is equal to 20, or you can choose n is equal to 100 also and calculate that. You can say, okay, that is the upper bound of the length of your string. So that's sort of some good observations is about how you can hear the length of the string from the eigenvalue of the equation. Okay, we will leave it here, but we will talk about this more in the next lecture. Okay, so we will be able to find the eigenvalue. So that's why I wrote that time that from the eigenvalues are really important for these questions, because this will tell you the how long the string is, you know, the what you are playing. Okay, so when we have the eigenvalue, what we need to do is we should write down the solution, you know. So now our solution is in this equation, x of x is a1 is equal to a2. So I'm gonna say a1 e raised to power lambda, square root of lambda, you know, it means the square root of that, the square root of minus n square pi square over L square time x. And that is again a1 e raised to power minus square root of minus n square pi square over L square. And then we have x here, okay. And we can do is we can pull out a1, and this is gonna be e raised to power I n pi over lx, and this is gonna be a minus e raised to power I n pi over lx. If I substitute the value of in term of sine and cosine and simplify, this is gonna be my answer. Sine n pi L over x. That's gonna be, you can verify that. So that is the solution x of x. What is a t? T of t is a b1 e raised to power lambda c time, you know, what is a t? T2, let's go back and look at what was a t. The solution of t is here, c times square root of lambda. So c times square root of lambda. What is the lambda? Minus n pi over L, the square of that time t, plus b to e raised to power minus c square root of lambda minus n square pi square over c square t. Do we need to simplify it? Maybe. So this is a b1 e raised to power c. So it's going to be a minus I c n pi over L t plus b to e raised to power. So this is a plus and this is a minus. I c n pi over L t. Yeah. Plus what do we have? X and t. So we can write down the solution now. So what I can do is a little bit, I can turn that thing into sine and cosine also. So let's not have the complex exponentials and turn everything into real. That will help us in the next, but we really don't need to do at this point, but we will see that this is going to help us. So this is going to be a b1. What is it? This thing is a cosine c n pi over L t plus I times sine c n pi over L t, and this plus b2 the cosine c n pi over L t minus I times sine c n pi over L t. And if I combine, then it's going to be a b1 plus b2 cosine c n pi over L t, and it's going to be a plus b1 minus I times b2. It's going to be a sine c n pi over L. Just like it. I can choose this one different constant if I want to, but I will keep that one here for now. But I can change that one in different constant as well. But you see that now these constant are complex exponential. This constant has a complex number, even thus doesn't have, but this one does have complex number. So just keep in mind that one. So what will be a solution? Because here we have an n, so I can write n here because each n will give you one solution. So same thing is n here, each one will give you one solution. So we got a family of solution. So u nxt, we have a family of solution which is a a1, so 2 times I, which is also depending on the complex number, sine, what was that? Sine n pi over Lx, and multiply by this function, which is b1, b2, and cosine c n pi over L t plus b1 minus I times b2. This is a sine c n pi over L t. I'm gonna move that constant inside, and I'm gonna write a bit more neatly. This is gonna be a sine n pi over Lx, and then you have a 2ai B1 B2 cosine Cn pi over Lt plus 2ai B1 minus I B2 sine Cn pi over Lt. I can choose these constant because each n will give you a one constant also. So what I'm gonna do is I'm gonna redefine these constant again. We're gonna say this is the an cosine Cn pi over Lt. So I choose this as a an, this is as a bn, and this is a bn sine Cn pi over Lt. So this is my family of solution. I have infinite number of solution. Each n will give me one solution. So, but this solution also depends on this two constant, an and bn. So each time I pull, I have to find a1 and b1. So it's still a general solution. It's not a particular solution which is satisfy these boundary condition. So now I'm gonna impose in order to find that. So I will write down by the principle of superpositions, because the sum of two solution is also a solution, because it's a linear ODE. If there are two solutions, their sum is also a solution. I'm gonna write this solution where n vary from 1 to infinity. I'm gonna add all the solution together, and this is gonna be a solution. So I'm interested in that solution, because for this solution I will be able to find that a1 bn. You will see in a minute. So this is the an cosine Cn pi over Lt plus Bn sine Cn pi over Lt. Okay. Now, okay, now it's moving. So this is the sort of general solution I have, where I have to impose the now the initial condition. Impose initial condition. What is the initial condition? U at x and 0 is equal to t, f of x. At time initial, the profile is this. If I impose that condition, so let's see what happened. So u x and 0, if I plug t is equal to 0 in my solution, what I'm going to get is going to get this is a sine n pi over lx. If I plug t is equal to 0, cosine of 0 is 1, but sine of 0 is 0, so I'm gonna get only a n here. So that means f of x is equal to, can be written as the initially n vary from 1 to infinity a n sine n pi over lx. And this is a Fourier series of f, on the interval 0 to L, I guess. Yeah. And so Fourier series has a unique representation. So therefore, a n will be, it will be 2 times 0 to L. This is 2 over L, I guess. Yeah, 2 over L, 0 to L, fx sine n pi lx. Yep. And so this is your an. So we was able to calculate the an in term of fx. If you have the initials, we can calculate the an of the solution, but we still need to know how to calculate the bn. So for the bn, we need to impose this condition ut. That's why we have a derivative with respect to t, and then x and 0 is equal to g of x. That's your another condition or restriction you have. So what is the u of t of the solution is first, x comma t. Gonna be a summation n vary from 1 to infinity sine n pi over L x, sine n pi over L x, and this the derivative of this function with respect to t. Derivative of this function with respect to t is gonna be a n c n pi over L. This is gonna turn into sine c n pi over L t with a negative sign also. And this is gonna be a b n c n pi over L. This is gonna turn into a cosine c n pi over L t. Now I plug t is equal to 0, so ut x comma 0 is equal to summation n vary from 1 to infinity. It's gonna be a sine n pi over Lx. This time if I plug 0 here, sine 0 is 0, so you're gonna only left with b and c n pi over L. But this one is given as a gx, so gx is equal to summation n vary from 1 to infinity b n c n pi over L divided by L. This time this is a sine series of the function g. So when the sine series of the function g is a uniquely representation, so b n c n pi over L can be calculated from 0 to L, 2 over L, and gx multiplied by sine n pi over Lx. This is the Fourier representation. So if I calculate bn is gonna be 2 over cn pi, because I multiply that one, divide over the other side, is gonna be 0 to L gx sine n pi over Lx and dx or dx. So this is your bn coefficient. So I'm gonna summarize this one. So this is a lot of derivation. So let's summarize this. So if you have a heat equation, the wave equation utt is equal to c square uxx, and you have the initial condition fx and initial condition of the velocity of the profile is equal to g of x, and the boundary condition that at boundary 0 anytime t and at L at any time t the string is a fix. Then the solution of this, the Fourier solution of this equation will look like this, and vary from 1 to infinity sine n pi over Lx, and then you have a an, which is a cosine c n pi over Lx plus bn sine c n pi over Lx, where an is equal to the integration from 0 to L 2 over L and fx sine n pi over L x, and bn is a bit different, is it 2 over 2 over Cn pi, Cn pi, and 0 to L, this time Gx sine n pi Lx dx. So this is your solution. This is the solution of our heat equation, the wave equation. Any question here? Because the derivation is kind of long, but it is almost the same way we did it in the heat equation. This is known as a separation of variable. I will do one example because that's your last homework is going to be on this topic. Let me find an example. It's on the book, 213 page. 13.
Professor.
Yep.
So technically, could we use this approach to solve number 3 on the homework?
Yes. Number 3 on the heat equation can be.
Okay.
But this is a wave. You can do the heat equation one the day before the lecture, which was.
But like the general approach is pretty similar.
Yeah, general approach is pretty similar. This approach to solve the heat equation and wave equation is pretty similar. The only problem, I think the wave is a bit more complicated in a way. The reason is that you have a two constant here. You know, when you wrote that in the heat, you will have only one term, but in the wave, it has a two term because it's a two order in time. This is the only difference, but other than that is same basically approach. Okay, I don't think they have any example in the book. Okay, let's make an example if they don't have any example in the book, which will be easier. Okay, you can look an example how do you basically solve that one. So when I say, whenever we basically write a homework problems, it's gonna let's do an example. Solve this wave UTT is equal to UXX and on. Seriously? Doesn't move anymore. Okay. Then U x0 is equal to, let's suppose, sine x. X d derivative of that is can we take sine again or we take cosine? Maybe let's take cosine of that. And then the boundary is u. I'm taking c as a 1. And the boundary you can take as 0 and x is equal to fixed, and then what is the period of 2 pi? 2 2 pi other way around. Is equal to 0. So what I'm doing is this, this is my 0, this is a 2 pi, and I'm taking that one sign, as initial condition. Okay. Sine pi by 2 is 1, so somewhere is a pi by 2. That's 1. So like that's how you pull it and you release it. Okay, let's see that. What will be the solution in this term? So u, x, and t, the solution is gonna be summation n vary from 1 to infinity. It's always gonna be how much integrations we have to do. Sine n pi divided by L. What is L? 2 pi, and then x, and then a n. This is a cosine. C is 1 n pi over L, which is a 2 pi, and x plus bn sine n pi divided by 2 pi over x. Okay, where a n is 2 over 2 pi, 0 to 2 pi, and fx is a sine x time sine n pi over 2 pi x dx. I just want to make the integration simple. That's why I choose that one. You see, this is a sine x, and this was a n pi over L. If you look at the solution, is n pi over L. So this become 1 over pi, and that become 0 to 2 pi, and this become sine x, and this becomes sine x divided by 2 dx. Now you need to use this formula in order to calculate this integration. You need to use sine A times sine B in term of what they called sine A plus B sine A minus B. Okay, I will leave that you to calculate what is the A n's are, because when you do the integration, are these function are I think all you need to do is when n by 2 is equal to 1, when n is equal to 2. I think the only term is going to survive is when n is equal to 2. All term might go to 0 because these signs are orthogonal to each other on 0 to 2 pi. But I will let you do this calculation. Bn, or I can use the computer to do that too also. It's going to be now Bn 2 over C is 1 n pi. So what is it? N pi, here there is no L. 0 to 2 pi. And the function gx is a cosine of x. And this is going to be a sine. And x divided by 2 x. And then you can calculate these integration. So let me find that formula actually. What is the sine A plus B if you really want to derive this integration, because it's a good sometime to do the integration. So what is the sine A plus B? Sine A plus B is sine A cosine B. There is a plus sign, I guess, in that case. and cosine A sine B, and then you have sine A minus B, which is a sine A cosine of B minus cosine A sine B. If you add them, so basically this is the formula I was talking about. You know, sine A plus B, and you are adding them. So you sine A minus B divided by 2. That's the formula of sine A cosine of B. So if you use that one, you know, I will calculate your Pn, but you have to calculate your An. So 2 over n pi. So this is going to be 0 to 2 pi. This is going to be a sine A plus B. So n x divided by 2 plus x plus sine this x minus n x divided by 2 divided by 2. That 2 cancel out. You have 1 over n pi, and then you have 0 to 2 pi. This becomes sine n plus 2 divided by 2 x, and this become plus sine. This is going to be a 2 minus n divided by 2 x dx. So you see that if n is equal to 2, this will go to 0. Yeah, if n is equal to, this is correct, yeah. Or if n is equal to negative 2, this goes, but n is equal to, n can be negative, we always choose positive. So for n is equal to 2, we'll do that calculation, it will be easier. So A2 will be 1 over 2 pi 0 to 2 pi. This is going to be a sine, if n is equal to 2, that gives you a sine 4. 4 divided by 2, that is a 2 sine 2x dx, and that gives you 0, which is 1 over 2 pi 0 to 2 pi sine 0 is 0 dx, you know. So that term is sine 0 is 0, and whatever this is a 2 pi, this is going to be a cosine, this is going to be cosine 2x divided by 2 0 to 2 pi. The value of the cosine is the same, so this whole entire thing is equal to 0 actually. Yeah. I think even for any values of n, this is going to be a cosine, and as long as you have because this is going to be even, and when you're going to plug 2 here, so you see that even integration of an is 1 over n pi. This is a cosine n plus 2 over 2 x. There's one thing of missing a negative sign, but that doesn't matter. This is a negative sign. And one thing we are integration of this thing is that's 2, that's fine, you know. Yeah. So the integration of that is negative sign n plus 2 over 2, that from 0 to 2 pi, and this one is going to be a same plus integration of this is a cosine 2 minus n divided by 2x divided by 2 minus n divided by 2 with a negative sign 0 to 2 pi. If you plug 2 pi here, you're going to get n plus 2 to the power 1 over n pi, and that's going to be a 2 over n plus 2, and you plug it here, it's going to be a cosine n plus 2 and pi, and minus cosine 0 is minus minus plus, cosine is 0 is 1. So you're going to get something like that here, and here is that. And what's about this one? This term is also plus 1 over n pi, and then you have 2 minus n in the 2 in the top, and then you have 2 minus n in the denominator. And then again you plug 2 here, is going to be a minus cosine 2 minus n pi, and then minus minus plus 1. You know? Yeah, that's you're going to get. This is a 1 plus 1, that's going to give you a 2. Oh, but there is a, this thing is in the front of that. So that. So, but what is this number? You know, so this number is a minus 1 to the power n plus 2. Minus is here, and that number is basically minus 1 to the power n plus 2. Yeah, this is your an look like. You know, so look like a really messy, but depending on. So minus 1 to the power n plus 2 plus 1. So many coefficients are 0 actually. N by 2 minus n. And this is a minus 1 to the power n 2 minus n. 2 minus n. So this is a 2 minus n. And pi plus 1. So this is your BAN or BN. Sorry, this is a BN, you know. So this is a BN, not AN. Yeah. And you can calculate AN also, because here you have sine A cos B, but here you have sine A sine B. You know, this is a different formula. Here you're going to have only n is equal to 2, 0, because here you have many n is equal to 0. So that's why these are like more coefficient here, but here maybe you have only few to 1. So this integration is a bit easier than the one I did. But all you can do is the one other thing you could have done